Okay, good morning everybody. I hope everybody had a wonderful weekend and hope you're having a beautiful day so far. So just a quick thing, I did put out assignment 5, so this is the final assignment. It'll be due by the end of December the 5th, so that's on a Sunday. I try to give you as much time as I could based on the scheduling I have. So just keep in mind that this doesn't necessarily match what's in the course outline, so I'm giving you more time. And one thing that we're marked about this one, on this assignment, I have you playing a little bit around with that fractional knapsack greeting algorithm in relation to fractional knapsack, but also 0-1 knapsack. There's a couple bonus marks associated with that. So do take a peek at that, and then after that you're using the recursion tree method to determine the asymptotic behavior of a given complexity function. And then there's going to be some problems involving this so-called simple master theorem I'm going to cover today, where you're going to be trying to use it and see if it applies. Sometimes it doesn't apply. That'll be for you to figure out. And then there's just a couple other ones after that, mainly one where I'm going to give you a divide and conquer algorithm, which I'm going to talk about what those are today. And where you're going to derive a running time for that based on the format I'm showing you in class today. And then finally, there's one other algorithm I'm going to ask you to execute it out. But we haven't quite got to that algorithm quite yet. It involves dynamic programming. We're going to be talking about dynamic programming in a little bit. But not today, not today. So anyways, with that being said, why don't we get started here today? So today I'm going to be first starting off with what I'm going to refer to as the simple master theorem. Now some people call this the master theorem, but I like to give it to students very often because it's very easy to apply, but at the same time it also has conditions that are also relatively easy to have applicable in often quite real scenarios. In fact, many algorithms that you've seen fit into the form of what we call the simple master theorem here. So I'll abbreviate it as SMT for abbreviation. And you might ask, why am I calling it a simple master theorem? It's because there's a more general one that I usually call the master theorem. That's actually going to be in the notes I'm going to post after class. I'm going to ask you to read that. So be aware that that exists, and I'm going to give some examples of using it there. So I want to talk about this so-called simple master theorem, and we're going to focus on that here. So suppose I have constants A, B, and S. So like there's going to be a bunch of constants here. And your job most of the time, because this is going to be effectively a cookbook approach to dealing with the asymptotic behavior of recurrence relations. So last day I showed you about recursion trees, and we talked a little bit at the end about how the recursion tree relates to the total amount of work that gets done overall, which gets represented as our big O or big theta result. So this theorem is going to capture what I've described last day, and I'll explain why in a moment. So I'm going to have these constants A and B. I'm going to have another pair of constants called D and K. Actually, I'm going to also need one more. I think I call it C. Let me see. I need C, D, and K. I knew I was missing one right here. So I'm going to have constants C, D, and K, where the constants are all going to be satisfying the following. That A is greater or equal to 1, B is greater or equal to 2, C is going to be positive, D is going to be greater or equal to 0, K is going to be greater or equal to 0. Just keep in mind the domains of these constants. And it must be, here's an additional constraint I'm going to throw in, but believe it or not, you can often get away with just making this assumption flat out, which is oftentimes when people state this version of the master theorem, they don't normally say this, but it's something I want you to be very particular about, at least with this class, is that N and S are going to be powers of B. So N and S are a power of B. So if I give you these constants, and suppose I give you a recurrence T of N, which is going to use these constants. So suppose it's eventually non-decreasing, so we talked about that the other day, and it is of the following form. So here's the form. So this should look quite similar to the one I showed you the other day, that T of N is equal to A times T of N over B. So you can think of this when you talk about a recursive algorithm. I'm taking the input N and I'm cleaving it up into sizes of N over B. So I have A of these. Quite similar to my example the other day with my recursion tree where I split it into 3 and each one was a half of the size of its original input. Plus some, what's going to tantamount to some term that's big theta of n to the k for any k greater or equal to 0. Well, so in this case, I have it where n is greater than s. So remember, n and s are powers of b, where I'm going to have a base case of t of s is equal to d. So you'll notice that if I have this, and typically we will work on the assumption that t of n is eventually non-decreasing, but if you ever find yourself needing to show this, you can always prove it using mathematical induction. But for this course, we're typically just going to assume that flat out. I won't give you weird things unless it's something I explicitly point out to you. So that being said, if it satisfies these properties, then I can tell you unconditionally respect of what n, like remember up here I restrict n to be a power of b. So this is just regardless. T of n, it has 3 cases that are possible here. So the first one is that if we look at the constant a, and it's less than b to the k, where b is another constant up here, and k is another constant, if that is satisfied, then we can say that t of n is big theta of n to the k. If it is the case that a is equal to b to the k, which we will call case 2, then it's something that looks polylogarithmic, the fancy name for basically me saying, well, this is one polylogarithmic function, where what I'm going to have here is that I have n to the k times log base b of n. Just keep in mind that that b, remember, I may have mentioned this explicitly before, if not, that b itself doesn't really matter in the asymptotic notation. It's just for the sake of ease for us to remember the form. And then there's this third case here. So if a is greater than b to the k, then I could tell you that t of n is big theta of n to the power of log base b of a. Now, when you look at this, so first, are there any questions about this statement in itself before I proceed to give you some intuition with it? So just keep in mind that A is telling you the number of splits are, yeah, this is quite a bit of stuff to look at, right? So just as a matter of expectation, I will expect you to know this theorem, just to be clear. So I'll give you some intuition to make this a little easier to remember. So remember last day I talked about how when we had our example where I was splitting and I was subdividing down in my pieces with my second example, I had it where I found out that the root was, like the work that was being done at the root or towards the top of the tree was dominating the running time of the entire algorithm, presuming that this recurrence relation represents the time complexity of said algorithm. So that's actually case 1 here. This is when at the root, most of the work is happening. And then what happens is as we go down the tree, the amount of work is decreasing. So that's why you'll notice that if a is less than b to the k, that just simply means that the amount of stuff that's happening at any one place is not going to dominate towards the top. Case 2, this is when you're going to have it where at every level of that tree, you're going to have proportionally equal amounts of work happening. That's why you'll notice that if you look at my function right here, this is the non-recursive work in the recursive case, right? So that's Cn to the k. So notice that this is saying if I were to tell you that the recursion tree's height is log base b of n, that at each level it's essentially doing big theta of n to the k. So that's where the recursive work, the splitting process is sort of, they're in balance with each other when it comes to the non-recursive work. So at every level, there's proportionally equal amounts of work happening. This third case, this is when the leaves end up doing most of the work. This is when you have a lot of leaves typically. That means the splitting, remember this is how many recursive calls you're making is going to be much bigger than even the forking off of all my subdivisions. So you can think of this as the root dominates the trees processing. This is when the leaves are dominating the running time. This is when they're in harmony with each other. Does that help a little bit with understanding what these three cases represent? So this is what I talked about last day, actually. So this actually naturally characterizes that. So this actually, you could get out of this theorem, if you actually wanted to try proving it, you can use the recursion tree method on each one of these cases and you can verify this. So just as a remark, like I said, you can replace this Cn to the k with big theta of n to the k. So if you were to write big theta n to the k here in more that informal way of talking about the asymptotic notations, that's okay too. So that means if that was written like that, you wouldn't have to present me what C is. It's implicit in the big theta notation. But yeah, so that's where these three cases exactly come from. And if you're curious, in the Master Theorem, this exact correspondence happens again. It's just more general what you can do with it. So for example, there's going to be some limitations of this theorem where you can't do certain things with it. I'll talk more about that after we go through some examples. So the big thing that you really want to take from this is that this is going to give you like a cookbook recipe. So if you can formulate your recurrence to look something like this, and it satisfies these constants and these conditions, then you can use the simple Master Theorem. So you're gonna see how dead simple this is going to be. So like I said, and I promised you, I was gonna give you something very easy that you can use. So here's the idea. So let me just do some examples with you. So I'm gonna do 3 examples, one illustrating each of the cases for the simple Master Theorem, okay? So I'm going to start off with something that looks rather cute. And it actually should kind of remind you of something that you've seen before with another recursive algorithm. So suppose I give you a recurrence relation T of n, where it's equal to T of n over 2 plus 1, where T of 1 is equal to 1 and n is a power of 2. So the first thing you can tell me right away is, okay, well, what we want to do is we need to identify those constants. So when we look back at that form I have there, I have an A, I have a B, I have a C, a D, and a K, right? So when I look at this recurrence relation, you want to identify what all those constants are. So it's going to be somewhere right about here. There's an A that you can implicitly say, okay, it's 1 times this. B is indeed greater or equal to 2, and it's an integer, so we're okay. Then you look for what C and K are. This usually relates to these two, to this term. Remember, it's the non-recursive work that happens in that recursive case. So your job is just to identify those constants and see if it fits the form of those conditions over there. So here's how I would approach this. So remember, n is a power of 2. So notice that the B here, 2, matches what I have over there. So the B is in fact 2. Notice that T of 1 is indeed, so 1 is a power of 2. And notice that we have all the conditions here. In fact, it's also worth noting that this is, of course, eventually non-decreasing, but we'll typically just presume this as a fact when we're playing around with this for the sake of this course. So here's how you could apply this. So we just simply apply the simple Master Theorem where A is equal to 1. So remember, I just make one recursive call. Sometimes it really helps when you look at it like a recursive algorithm. So think about it in your head like I give you some algorithm where one recursive call happens, and what it will do is it considers something like half the input. So it subdivides the problem into half of it. And then it does some constant amount of work. So I have A is 1, B is 2, C is 1. So notice that it's just 1 here. So notice that if I wanted to have Cn to the k, if I make k is equal to 0, then I end up with n to the 0, which is just 1. So then I just say, okay, C is 1, k is 0. and I just say d is 1. Remember, the whole idea is that this base case of my recurrence right here, it will typically be a constant, and that's reflected in this simple master theorem. So all I'm going to do now is I need to figure out what case I use once I've identified these constants. So notice that a is equal to b to the k. This is because 1 is equal. So I'm just going to put what a and b to the k are. So when you're doing this, you just see what a and b to the k are and see if it's equal, if one is less than, or one is greater than the other. And that's how you determine the case. So since they're equal, because 1 is equal to 2 to the power of 0, we apply case 2. That's the one right in the middle. So what does this say? So if you plug in everything into the second case, you end up with, remember, it's that t of n is big theta of n to the k times log base b of n. So I'm just plugging in the constants I have here. So it's n to the 0 times log base 2 of n. So what's n to the 0, everybody? What's n to the 0 again, everybody? What's n to the 0? It's just 1, right? So that means that it's just going to be, therefore, that t of n is big theta of log n. Now, if you think about what I described up here as this recurrence relation, this should remind you of an actual algorithm you've seen before. If you were to try to formulate a recurrence relation for this algorithm, you would end up actually with this time complexity. So the one I'm suggesting for you is that if you assumed n was a power of 2, then the above recurrence actually matches what you would analyze for binary search. If you didn't make the assumption that n is a power of 2, you would typically have it where there's a floor function on n over 2 in there, just to ensure that you're not like ending up with something that isn't an integer. But one thing I want to remark about this, and this is actually a feature of this master theorem, I want to come back over here. I'll come right back over here because I still have to do another example with you, but I want to reiterate something that I mentioned the other day, and I talked about this concept of smoothness, right? I talked about smoothness. So, come on, camera, we're over here. Okay. So, I think this is good enough. So, when I have my cases here, and I told you that t of n is big theta of that unconditionally. Do you see the conditions of smoothness here? It's actually because, like I told you, a polynomial that looks like this is smooth. This is also technically a polynomial as well. That's also smooth. And you can actually prove that this is also smooth for some constant k. So that's actually the underlying theory that's actually getting you this result here at the end, without where n is a power of b at the end of this. So typically when you're using this in your analysis, what you do is you assume, okay, n is a power of 2 or n is a power of 3 to make it so it's a little easier to work with. And then when you apply this simple master theorem, all you have to do is you get essentially this for free because all of these are smooth. So remember the conditions of the smoothness rule? So remember the smoothness rule said, okay, if f is this and g is smooth, then you could essentially apply something akin to this statement over here. So if you're wondering about how that's possible, that's actually the underlying reason why. It's the smoothness that makes this possible. So I just wanted to make sure I remarked about that because it's a really slick idea. That's actually why I showed you that concept the other lecture. So that it doesn't seem like complete black magic why I wrote this. Because there's a couple different ways you can derive this theorem, but you can show that each one of those resulting functions is smooth. Okay. So first, is everybody okay with this example? Because if we're okay, let's do another one. You're going to see once I've done this at least once, you're going to see hopefully the pattern here. So the first thing I always do is I see if the recurrence relation follows the pattern that I have over there for the simple master theorem. So here's another example. Suppose I give you t of n is equal to 3t n over 4 plus 3n squared, where t of 16 is equal to 1 and n is a power of 4. Now, just as a small remark, you can't always have it where there's smaller terms like t of 0 or t of 1 or other things like that. That's also okay. So somebody's asking about d. It says d is 1 here in this example. So remember, d is going to end up being the term that's going to represent the non-recursive work that happens in the base case, which simply just means the number of operations that happen in the base case. So in this example here, all I do is I pick out the constants. See, a is 3, b is 4, c is 3, and k is 2, and d is 1. And then I look at what a and b. I compare those with that exponent k. And I notice that a is in fact less than b to the k because b is 4 and k is 2. So that means I'm going to have 3 versus 4 squared, and 4 squared is definitely larger than 3. So what case is this? This is actually just case 1. So when you do that, you just simply notice, hey, look, all that work that's happening is all happening right at the beginning of this whole process, mostly. So since k is 2, we apply the first case, which just simply says the t of n is big theta of n squared. Does this one seem pretty okay? Is this a little easier than having to draw out that recursion tree and counting up all the work yourself? Give me a thumbs up if you think that. Yeah, this is like I said, it's very cookbookish. So if you find the properties that you're looking for, most of the recurrence relations you're going to run into when you're analyzing these so-called divide and conquer algorithms, a lot of recursive algorithms, they'll fall into this cookbook recipe, a lot of them. That's why I showed you the recursion tree method, because sometimes it doesn't really happen very well. Like my first example where I decrement down by 1 every single time. Notice that the simple master theorem's recurrence doesn't actually look like that. So I wanted to show you another way you can tackle those. Okay, so if we're okay with this, I'm going to proceed to do, okay, so do we need to state the theorem every time? Can we just say using SMT? So what I would like you to, this is what I recommend doing, because remember, the simple master theorem is indeed a theorem. So at some point you need to invoke it somewhere. So you could say using simple master theorem, we see a is equal to this, this, and this, and this. That's okay. So somewhere you need to acknowledge where you're using the simple master theorem. That's all you really need to do. Hopefully that's clear. So sometimes you'll see that I say, oh, so we apply the simple master theorem, or I say by the simple master theorem. At some point I need to invoke that, because otherwise it just sort of comes out of thin air, right? Like, okay, well, where'd the result come from? It came from the simple master theorem. Hopefully that clarifies that. Okay, so let's do one more example. And be rest assured you're going to get plenty of practice with this simple master theorem on the assignment. I'll give you a few more to play around with there. So here's one more. And then we're going to talk about something a little different. But it's actually quite closely related to what I'm talking about here. So, excellent. So for example, we would say by simple master theorem case 1, we have, if you were to identify the constants and then you just say by the simple master theorem case 1, we have blank, that's all good. That's wonderful. So your job is just to remember to identify what those constants are. That's usually the main game in town, is figuring out what those constants are. Sometimes I must remark, as you're going to see at some point during this lecture, that if I were to write big theta of one of these instead of the c times n to the something, you may not actually technically have a C that you pick, you just implicit in the definition of the recurrence. So in cases like that, you won't give C, you'll just say, okay, there is some C. Okay, so let's do one more example. Here's another example. So let's consider T of n is equal to 9t n over 3 plus n, where t of 3 is equal to 3, and n is a power of 3. Okay, so you guys are going to help me with this one. So I'm going to say we see A is equal to what? What is A? What's A here? Let's see. Can somebody tell me what A is? It's 9, exactly. Though my A looks kind of like a 9. A is 9. Okay, B. What's B? Somebody tell me what's B. It's 3, exactly, exactly. C, somebody tell me what C is. Yeah, it's just 1. Okay, how about K? Yeah, it's 1. See, everybody's just, I'm loving the chat right now. You guys are getting this. That's awesome. You guys are pros at this. And how about D? What's D? There we go. We see just, you just put 3 in there. Perfect. And as, now, you'll notice that A is actually going to be greater than B to the K. As 9, so if I give you 9, so look, we have B, which is 3, K is 1, so most certainly 9 is going to be bigger than 3 to the 1, right? So we have the third case, exactly. We have case 3. Then we just theta of n to the log base 3 of 9. And then by the simple Master Theorem, what's the final result, everybody? What is the big theta in? I'll give you a hint, it's n to the something. Why we apply the third case? So if we have the third case, this is when we have it where, let me just, for dramatic purposes, remember, we apply the third case when A is in fact greater than B to the K. So that's when we apply the third case. So this simply means, if you look at this is quite natural if you look at this recurrence relation. Look how many times that this is recursively culling on smaller pieces. There's a lot of those. So that means it's going to reflect itself as many, many leaves in the recursion tree. So let's think about it. So we have log base 3 of 9. So think about it. What exponent do I need so that it's 3 to the something is equal to 9? Yeah, it's 2, right? So n squared. Very good. Very good. Wonderful. So, believe it or not, that's all I have to really say about the simple Master Theorem. Are there any questions before we proceed? Oh yeah, one other remark I'll make after if there's any other questions. Okay. So if we're okay with this, I want to make one remark. So this is just more of a warning than a remark, really. The simple Master Theorem has a specific form a specific form and permits certain constants. So just be very careful because sometimes you can't apply the simple master theorem. So here's an example of something you cannot use the simple master theorem on. So suppose I gave you t of n is equal to 2 to the power of n times t of n over 2 with the floor plus 1 if n is greater than 1, and t of 1 is equal to 2, where n is a power of 2. So here's an example of a strange-looking recurrence relation. Let me just, so this is just a t, just to be clear. So does anybody have any ideas of why I can't use the simple master theorem on this recurrence relation? And I did do something deliberately to throw you off. So just, I'm hoping that you see what's the most important thing here. Yeah, a is not a constant. So notice right here, this is what's supposed to be a in our form. This is supposed to be a constant, not a function of n. You might ask, Dan, well, what about this floor function you applied to n over 2? Believe it or not, the way this is written, that floor actually doesn't matter at all. Because n is a power of 2. So if you plug in a power of 2, and you were to say, for example, suppose I gave you, say, 2. 2 divided by 2 it's going to be cleanly dividing the number, right? And we have a base case already for 1. So if I give you powers of 2, like 2, 4, 8, 16, and so on, notice every single time the floor function doesn't matter really at all. We don't have to round down anything because it's always just going to be an integer. So this is just a matter of redundancy when I write this when n is a power of 2. Often when you're doing your analysis, before you make any assumptions about n being a power of 2, sometimes you end up with these floor signs like this. But if you make, without loss of generality, the assumption that n is a power of 2, you don't have to worry about those floors or ceiling functions, typically when you're devising these recurrence relations. Okay? So just be warned, because on the assignment, I'm going to ask you to look at different recurrence relations. So if n was a power of 3, however, now we have two issues here. So if n was a power of 3, and suppose it looked like n over 2 like this, remember the form of the master theorem requires that n is a power of b, where b would be sitting right here. But there is actually a more general version of this master theorem that permits me to not even care about what n is with respect to b. So I'll ask you to take a look at that. It's actually even more general, but its conditions are a little harder to demonstrate or prove. But it's very similar and very cookbookish as well. There's just one of the cases that's kind of nasty. But you can cover all sorts of other cases, such as, notice that in ours, the non-recursive work always reflects a polynomial. So if I were to give you, say, that f of n, the non-recursive work in the recursive case, suppose that was not a polynomial. Say it was, say, n factorial. You cannot use the simple master theorem on this because there is no polynomial that has the same rate of growth as n factorial. But however, there is, for the master theorem, you can most certainly apply it, which is, I actually have an example that's going to be in the notes that shows you how you do this. Okay. Yeah, so it would be the floor of n over 3 where n is a power of 3. Exactly. So just be very careful when you're applying this simple master theorem. So these make very good exam kind of questions, just to give you a heads up. So anyways, if we're good with this, I want to move on to talking about what a divide and conquer algorithm is. So let's proceed over to this board over here. And believe it or not, I don't actually have a whole lot to say about divide and conquer algorithms. Because you, believe it or not, you've actually seen plenty of them actually already. But I mean like way beyond just like before we even got to this course. So you're going to find that I'm just going to describe what a divide and conquer algorithm is. And then I'm going to give you a way of looking at the divide and conquer algorithm with respect to the simple master theorem. Or just the master theorem more broadly. So these are a particular kind of recursive algorithm that has a very specific kind of form to it. So you can look at this as another algorithm design technique. So divide and conquer algorithms. So here's the idea of, and I'll usually abbreviate this as D and C, just for the sake of this lecture, because it's a lot easier to write down. So D and C is an algorithm design technique that expresses the solution to a given problem in terms of solutions of similar but smaller subproblems that can be solved independently. So just to give you an idea of what the algorithm exactly is going to do, the algorithm breaks the problem. When I mean problem, I'm referring to its instance, of course, not just like, we're not taking the whole space of all of the problem instances. I'm talking about a given instance of that problem. Breaks the problem into smaller subproblems. Solves the subproblems. And then puts them together to solve the original problem. So the name divide and conquer comes from the fact that the algorithm will divide the problem instance into smaller and smaller and smaller subproblems. Ideally, when you think about it, when it reaches that base case. And then what it does is it puts together all of those solved problems to solve the overall problem. That's the conquer part of divide and conquer. So divide means split it into smaller and smaller subproblems. The conquer part is that you take all of those subproblems in some way to construct a solution for the overall problem. So here's some examples. You've actually seen plenty of these. So for example, I'm going to talk about merge sort in a moment, but that's a pretty good example of one. You've seen binary search. I mentioned that a moment ago. This one's not as interesting if you think about it as a divide and conquer algorithm, because we always like, you could think of it as, I suppose I have it where I'm searching in my array for some element, And you have it, okay, so conceptually the idea was very simple. You have that middle position, and then you have it where you consider either the left side or the right side. In a divide and conquer context, what you would do is you would just basically say, okay, whatever on the right side is just whatever, I'm just going to ignore that, and I proceed to search only the side that has potentially the key I'm looking for. So that one is a little bit different than this. This is quite natural as a divide and conquer algorithm. I'm going to talk about that one in a moment. You might also know quick sort, of course. We've talked about that one. So divide and conquer algorithms are natural to describe as recursive algorithms, but in practice, typically what you do is you try to translate it into an iterative algorithm that doesn't use that recursion, because depending on your performance requirements, you might have it where if you're making a lot of recursive calls, it makes your call stack really, really high. So just be aware of that. So for someone like me or you, when we're studying algorithms, it's a very natural way of describing the divide and conquer algorithm. But sometimes you may want to optimize further by trying to eliminate that if possible. So I'm going to give you a template, and then we're going to talk about how we use this for something like merge sort. And I'm not even kidding, it's going to be very nice and natural. So if I just gave you a divide and conquer algorithm, all you have to do is identify the bits and pieces to determine its running time, believe it or not. Like I said, it's going to be very natural. So hopefully everything I've been doing up to this point will feel very natural. So I'm going to give you a template for a divide and conquer algorithm. So this should hopefully give you an idea of what one of these looks like. So if you didn't like my description over there, you may find this very helpful. Okay, so here's a template for a divide and conquer algorithm. So you can think of this as a way, if you were to try to fit an algorithm into this template, this is what we would typically call a divide and conquer algorithm. So suppose I call it, say the algorithm is called DC, and it takes in instance X. I'm not going to worry about input, output. It's just going to be some template here. So if X is sufficiently small, or simple, if X is sufficiently small or simple, then solve it directly. Solve it directly and return. So you return a solution. So that's going to be, this is tantamount to your base case, okay? So this is going to be your base case, typically. So there's that happens. If that isn't the case, then you're just going to decompose. You decompose X into smaller instances. X1, X2, all the way up to some xk. And then we're going to have a loop. I'm going to write this in a way that, just so that you see it, for I is equal to 1 to k, we're going to do the following. So for each of these, I'm going to get a solution from the divide and conquer algorithm given xi. So I decompose it into these smaller pieces. Then I recursively apply DC on the smaller instance. And when I'm done the for loop, then all I do is I combine the yi's somehow to obtain a solution y for x. And then you just return y. So this would be a general template for a divide and conquer algorithm. So I want to give you a quick example, and then I'm going to do one visualization for you. So let me just quickly, so first, here's our template here. I'm going to have more details in the notes about this, but the big things I want you to point out here are that if you want to look at our recurrence relation that we formulated before, so if I give you T of n is equal to A T of n over B plus F of n, if you look at this, the A is going to be the number of times we split it into a smaller piece. N over B is going to be the size of that piece. And then F of n is going to be the work that happens around here. So I'll have more details about this in the notes, just for the sake of time. But my point is that if it follows this template, generally there's a way you can derive it as a recurrence relation that looks like this. So I want to quickly kind of give you an idea of what I mean by this. So first, is everybody okay with this? So this is just me describing what I wrote over there, just in a pseudocode-like way. So if we're okay with that, I'm going to quickly give you an example of me adapting this template. Then I want to just do one final example, just to kind of hammer in just the whole idea of a recursive algorithm and how its running time gets affected by this recursion. So here's an example with merge sort. So you may recall merge sort. It works kind of like this. So suppose I give you the algorithm, and we'll call it merge sort. It has an array A, it has a start and an end, where these are going to represent the starts and ends of the part of the array you're interested in. I'm not going to worry for the sake of time about the input and output. I'll have this in the notes. So if we find out that we have no more elements to consider, then we just simply return. So this is going to be implicitly the base case. Otherwise, we're just going to compute some mid, which is going to be the start plus the end divided by 2, applying the floor. And then what we do is, so you may recall merge sort, we have two recursive calls that happen, right? So we have merge sort. So you take the input array A, and you go from start to mid. This cuts it right about the middle. And then we have another merge sort call that's going to take A, mid plus 1, all the way to the end. So this is your left half. And the right half. Sorry, I just want to make sure I get this done in a reasonable time here. And then lastly, there's that method called merge, or function merge, depending on how you implement this, which takes start, mid, and end. For our purposes, all you need to know is that this takes big theta n time. If you're not sure about this, see CS210. It takes linear time. So this is the description of merge sort. Notice that it has this is our base case. Then what I do is I subdivide the problem into 2 pieces. And for each one of those, I solve them all the way down until I get to some sufficiently small case. Whoops, I need to put a 1 right here. My apologies. And then what we do is we merge those subarrays. So just if you need to remind yourself of merge sort, just take a look at your CS210 notes. But the point here is that it computes this and breaks it into 2 pieces. So we have 2 recursive calls. Each is of size n over 2, if n is the length of this array. And then we have some non-recursive work that happens, which is linear, like this. So you can formulate this as a recurrence relation that looks like this. T of 2 Tn over 2 plus big theta of n. where t of 1 is equal to 1. Because when I have the base case, I just check that condition and I'm done, right? That's why we have it where it's equal 1 there. So you might ask, okay, what is this for the simple master theorem? I'm going to have all the details in the notes, but this should match exactly your intuition. If you try using the simple master theorem, you're going to end up with case 2. And you end up with the big theta n log n time that you're used to. So just to illustrate this idea, because this is the last bit of me talking about this type of approach. Now, I could show you a fun demonstration if you give me 1 minute. Is that okay with everybody? Because I'm going to show you one demonstration and then I'm leaving for you for the day. But I promise you it's very fun. I only get to show this to some students. So I want to make sure I get a chance to show you this, because students usually like this demonstration. Okay. So if I'm not getting any pushback, but if you have to go, please go. You can always check it out in the video afterwards, okay? So I'm going to quickly do this just to illustrate the idea of how the running time for merge sort comes about, okay? Because sometimes people ask, Dan, where exactly does this recursive work really, like how does this manifest itself as like operations that happen? And I usually like to use a block of cheese. So imagine this is the running time of merge sort. So suppose I have my input and say, for example, the length of the array was say 8. So if you think about it like that, if you were to work out the recursion tree, you'll end up with 4 levels if my memory serves me correctly. But essentially what's going to happen is you're going to have these 2 recursive calls that happen, and then there's some linear amount of work. So if you look at t of n, remember, t of n represents all of the running time for t of 8. So I have a lovely, lovely knife here to help me out with this. So I'm going to describe to you what the non-recursive work is for our first recursive call. So this, for example, is that linear amount of work that happens when I initially call t of 8. Then 2 recursive calls happen. So 2 recursive calls happen. And each one of those, the non-recursive work is linear in the length. These are our 2 recursive calls right here. So if you're looking at the running time, this is so far how long we've been executing, with the presumption that we completed this at the end. So now, when each one of those 2 halves are applied, 4 recursive calls are going to happen. So I'm going to end up with 4 pieces of cheese. They're all going to be equally sized. So each one of the recursive calls on my next smallest chunk is going to look like this. And those, actually, yeah, we're okay. So I have 4 pieces here. Notice that all of these pieces each, so my chunk here, this chunk here, and these chunks here are all of actual equal size. If you actually work out the recursion tree, this will be exactly how it plays out for merge sort. And then you end up with this last piece. This will actually get subdivided into exactly 8 slices, and those are all of your t of 1s. So if you look at the overall running time, that is exactly how long it would take for t of 8. Visualize this cheese. So hopefully you found that a little bit helpful. And yes, if I was doing this in person, I would bring some crackers or something. You can have some crackers and cheese. If anybody had anything else, I would happily bring some couple other things that are for those that maybe can't necessarily have cheese. Yeah, no, definitely. So anyways, with that being said, hopefully this helps visualize a little bit of how that recursion actually turns into an overall running time like we had with our recursion tree. So that being said, when we come back, we'll talk about another algorithm design technique. So I'll say thank you very much and have yourself a beautiful day. I'll see you later.